All right, everyone. Welcome to problem 3.15 of David Griffiths Electrodynamics. So this one's going to be a fun problem. Essentially, we have a rectangular pipe where the x-axis is this way, the y-axis is vertical, and the z-axis is coming out of the board, and the rectangular pipe is running parallel to the z-axis. And it goes from negative infinity to positive infinity. We're just kind of looking at a cross-section here of the pipe. The pipe has three grounded sides, so the grounded sides are at y equal to 0, y equal to a, where a is a vertical height on the y-axis, and x equal to 0, so this side. So basically this side, and this side are grounded, and this side is held at a potential, some specified potential. It doesn't tell us, which is v naught of y, so it's a function of y. So the potential varies as a function of y along, it doesn't give us a specified potential yet. So part A is to develop a general formula for the potential inside the pipe, and then part B says to find the potential explicitly for the case that v naught of, in the case of the potential here, is just a constant potential. So that's basically it from the book. We have a lot of math to go through. So essentially what we're doing here is I've written out our boundary conditions given to us. So at x equals 0, the potential is 0. At y equals to 0, the potential is 0. At y equals to a, the potential is 0. And at x equal to b, where b is the where this side starts, the potential is some function of y. And so this is just a two-dimensional problem here. We're basically solving Laplace's equation in Cartesian coordinates for 2 dimensions. So I'm going to quickly go through this. David Griffiths has an example in his book where he goes through this even better than I do here. So I'll just quickly brush through this part and kind of get to the interesting stuff. So if you don't know how to solve Laplace's equation, essentially you use a technique called separation of variables. And so we assume a solution. So the solution, v as a function of x and y, we just assume that a solution exists in this form. So we have some function x as a function of x multiplied by a function y as a function of y. So we're essentially assuming that a solution exists where you have two functions independent of each other multiplied together, and we're just assuming that exists. So plugging this kind of solution into the equation, I'm kind of using shorthand notation here, so I'm using the actual function names here. I'm not writing out the function parameters, but if you plug this into here, you get the second derivative of x, y plus y second derivative times x equal to 0. Then from here, you divide by the original solution across on both sides, and then that just leaves you this term here. So you have x double prime divided by x plus y double prime divided by y equal to 0. And essentially now, this is a function only in terms of x plus some function in terms of y equal to 0. So what this implies is that both of these terms here are constants, because for those two things that equal to 0, they're independent of each other. So if you change the value of one, for them to both add to 0, the other one has to change by the same amount to still add up to 0. So this implies that those two things are just constants, so we'll call this term C1 and this term C2. They're just two constants. And then what you do is we just assume that C1 takes the form of a constant. We'll say it's k squared, and then so plugging that in and multiplying x over, and then what we have is x double prime equal to k squared x, and then doing the same too for C2. In order for those to add to 0, though, if C1 is k squared, then C2 needs to be minus k squared so that they can still add to 0. And we have y double prime equal to minus k squared y. And so essentially what we've created here is we've separated this partial differential equation into two ordinary differential equations. So I'm not really going to go through the details here on solving the ODEs, but the first one, the x function, is x double prime minus k squared x equal to 0. You use a common technique here where we let x equal this exponential function, so I say x is equal to e to the lambda x, and then plugging that in, you get this characteristic equation, and essentially we find that the solutions for this ordinary differential equation is a superposition of these two functions. So you have a e to the kx plus b e to the minus kx. If you guys are rusty on solving ODEs, then I suggest that you guys go find a video on YouTube for ODEs. I mean, this problem is so common in physics, or this equation is so common in physics, that like you should just know the solution off the top of your head. It comes up all the time. Like these forms come up all the time when solving like spring problems and whatnot. So these are very common ODEs. And there's plenty of videos here. I'm just here to explain the more interesting aspects of this problem. So then you solve the y ODE. So doing the same thing, we let y equal e to the gamma y, and plugging that in, and essentially what we get is the y function takes this form. So it's some constant c times sine of ky plus some constant e times cosine of ky. So we have these two functions here, y and x, which those are our two functions, which we said multiplying those two together gives us our potential v. So essentially up here, our potential function is just multiplying our two solutions here. We get a e to the kx plus b e to the minus kx times the y function. So now we're at the interesting part. So we apply our boundary conditions. So let's apply the first boundary condition here. So if you plug in 0 for x, our potential function reduces to, well, e to the 0 is just 1, so those exponential functions become 1. The y part doesn't change, so we get a plus b, that's just a constant, times this sine cosine function here, still equal to 0. There's not much here we can do, so I kind of just leave this alone for a second and take a look at the next boundary condition. So if we plug in y equal to 0, what does that tell us? Well, the x function stays the same, and if you plug in 0 for y here, sine of 0 is 0, so we're just left with d cosine of ky, or I should say this is k of 0, and so we're just left with cosine of 0 is 1, so we're just left with this times d, and so this can't be 0 because these are exponential functions, so that implies that d must be 0. So from our original solution, essentially we've gotten rid of this part of the solution because d is 0, so due to our boundary condition, so we're just left with this part at least. Going back to this part though, if d is 0, then we're just left with, and we use this boundary condition again, the first one, then we're left with a plus b times c sine of ky equal to 0. And so this just implies that, well, there's no reason that this section should be 0 because it's a function of y. I mean, sure, it can be 0 at certain values, but it's not always 0. So that implies that a plus b must be equal to 0. And so that means that a is just equal to negative b. So that's, this is what our first boundary condition tells us. Then applying the third boundary condition, where y is a. So we know that a is negative b, so in place of a, I just write negative b. So we have negative b e to the kx plus b e to the minus kx times c sine of ka, because remember y is a for this boundary condition, and that's equal to 0. So factor out the negative b, we have e to the kx minus e to the minus kx times c sine of ka equals 0. So this exponential part's not 0. And this implies that sine of ka must be equal to 0, and the only time that sine is equal to 0 is for integer multiples of pi. So that implies that ka must be equal to some integer multiple of pi. So in pi, where n is some integer 1, 2, 3, etc. And so that tells us that k is just m pi over a. So that's kind of what our third boundary condition tells us. So now we've applied those 3 boundary conditions. So let's just see what our potential function now is after that. So we have our minus b still. So basically, because a is just negative b, I factor out the minus b, and then the c from this part. Remember, we don't have this part anymore because of that. But the c I just pull out as well in front, so we have minus bc, that's just some constants. Then we have e to the kx minus e to the minus kx from here. And then we have, sine of n pi y over a, because k, in this case, we saw is just n pi over a. So we just replace the ky there with n pi y over a. And so this is our solution. If we take this term though, this term is just, there's an expression for the trigonometric functions and the hyperbolic trig functions. You can express them in terms of exponential functions. So this is just the same as 2 times the expression for sine, hyperbolic sine. And in terms of exponential functions, if you're confused about what I'm saying here, if you look up online, if you just look up the exponential form for hyperbolic sine, you'll see what I mean. So this is just 2 times if we divide this by 2, we'll have the hyperbolic sine function. So yeah, so we can replace this with 2. So I have a 2 out front now, times hyperbolic sine, and then everything else stays the same, essentially. So if you're confused about how I got from this function to the hyperbolic sine, just look up the exponential form for hyperbolic sine. And then from here, this is our general solution for our equation here. So this is it, but, well, I guess more realistically, this is a specific solution for some value of n. If we want the most general solution, then we take a superposition of all those solutions and add them together. So really the most general form is taking a summation from n equals 1 to infinity of this solution here. So some coefficients c sub n. So like the minus 2bc just get kind of absorbed into this coefficient. And then we have the sine, hyperbolic sine of n pi x over a times sine of n pi y over a, and that is our general solution. So that is really part A. Well, not quite, because we still have to figure out how to express c sub n here. So that's where our 4th boundary condition comes into play. So plugging in b for x, we get this sort of equation here. So we have the sum from n equals 1 to infinity of c sub n hyperbolic sine of n pi b over a. So now hyperbolic sine of n pi b over a, that's just a constant, because n pi is a constant, b is a constant, a is a constant, it's all a constant. And then we have sine of n pi y over a, and this is equal to some function of y. So then here we use something called Fourier's trick. If you're unfamiliar with Fourier's trick, again, David Griffiths explains this in his book. So what we're doing here is essentially using a property of the trig functions, the orthogonality of the sine function here, to sort of solve for our coefficient. So again, David Griffiths explains this in the book if you're kind of curious about it, but essentially what we do is we multiply both sides by sine of n prime pi y over a, and then integrate both sides from 0 to a. And this is valid because we're doing the same to both sides. And we're multiplying, so we already have sine of n pi y over a, but we're multiplying by the sine of n prime pi y over a, where n prime is not necessarily equal to n. So we can do that, and essentially we can rearrange this. So this right side I've moved over, so we still have the sum n equals 1 to infinity, c sub n, and then the hyperbolic constant term, and then you see I have a over 2. So in the book, David Griffiths already solves this, but if you integrate 0 to a for sine of n pi y over a times sine of n prime pi y over a, what you get is, you get 0 for, I think it's like either even or odd numbers at n, and then you get a over 2 for the other one. So essentially, we're eliminating certain values of n here, but this integral, removing the constant terms, just integrating the sine terms here, you get a over 2 or 0, depending on what value n is. And so that's the left side here, and then I've equal to this side, I've kind of moved it over. We're still integrating from 0 to a of this function v naught of y times sine of n pi y over a. Oh, I forgot to mention, so it's not if n is odd or even, it's this integral, when you integrate sine of n pi y over a times sine of n prime pi y over a, what happens is when n and n prime are equal, that integral is a over 2. When n and n prime are not equal, then they're 0. So we've essentially eliminated the entire summation down to a single term, because every term in the summation is 0, except for when n and n prime are equal. So that's why we're just left with this over here, and then I don't know why I still have the summation. I need to get rid of that. Don't know where I put my eraser though. Here it is. I accidentally still wrote the summation here on the side. We've effectively canceled every term here except for when n is equal to n prime. And this is still equal to the integral of 0 to a of this side, v naught of y times sine of n pi y over a with respect to y. And so just dividing all the constant terms over, then our coefficient is 2 divided by a times hyperbolic sine of n pi b over a times the integral from 0 to a of sine of n pi y over a times whatever this function is, v naught of y, with respect to y. So with this, we now have our general solution for this problem, which satisfies part A of this problem. So again, just reiterating, what we have is, we have this solution for our problem, where c sub n is given by this equation. Now, part B says to find the explicit solution for the case that the potential function along this side, v naught of y, is just a constant potential v naught. So down here, for v naught of y is equal to just some constant v naught, then we need to solve what our coefficients are. So here, c sub n, again, is just 2 over a times hyperbolic sine. I'm not going to say the arguments, but you can see it's just n pi b over a each time, times v naught. So we pulled v naught out of the integral because it's a constant, and then this just becomes an integral of sine with respect to y. And the integral sine is negative cosine, so we have negative cosine n pi y over a, and then because we have n pi y over a inside the argument, we divide by n pi y over a, or we divide by n pi over a, so then that flips to a over n pi here. And then we're still evaluating bounds from 0 to a. So plugging all that in, we have the negative comes out front. We have negative 2 v naught divided by hyperbolic sine of n pi b over a. The a down here and the a up here cancel. And we have the 1 over n pi. And then the only terms that depend on y is the cosine, so I have a bracket here. And then plugging in the bounds, we have cosine of n pi when we have y equal to a, minus cosine of 0. And so I had to kind of move from here, because I ran out of room, to over here. So our coefficient is negative 2 v naught over n pi hyperbolic sine. And in the parentheses, we have, well, cosine of n pi for n being odd numbers. We're actually not odd or even, but basically you can think of cosine of n pi, well, for each n, you get either 1 or negative 1. It just kind of alternates. So you can express that as negative 1 to the nth power. So if you just plug in values at n, when n is 1, that's -1. When n is 2, it's 1. When n is 3, it's -1, so it just alternates there. So that's another way to express this cosine of n pi term. It's just -1 to the nth power. And then cosine of 0 is just 1, so we have -1. Oops. And so what we have here now is, depending on if n is odd or even, well, if n is even, then this is 1, so this term becomes 1 minus 1, which is 0, and so the whole coefficient is 0. So when n is even, we have 0. When n is odd, then this is a -1, and so we have -1 minus 1, which is -2. So then what we have is -2 times this -2 out here, and we just have 4. So when n is odd, we have 4 v naught over n pi hyperbolic sine. And so this is our coefficient, so just plugging that into our general solution up here. What we have for our explicit solution for a constant potential is v of xy is 4 v naught over pi, because those don't depend on n. Then the summation over odd integers of n of hyperbolic sine of n pi x over a times sine of n pi y over a, all divided by n times hyperbolic sine of n pi b over a. So that all that hyperbolic sine stuff and the n pi and stuff comes from our constants, and then the rest is just from our general solution. So this is the explicit solution for the case where the side over here is held at a constant potential. So that is the problem. If you guys have any questions or some mistakes or clarifications that you need, please let me know in the comments below. Yeah, I really enjoyed this problem, so I had a lot of fun with it. It was a lot of work, but if you guys, yeah, I guess I'll see you guys on the next problem.